Okay. Hello, everyone. This is a TCS seminar at the Jagiellonian. Today, our speaker is Ugo Giocanti. Ugo finished PhD last year in Grenoble at the combinatorial optimization group, but most of his work is, I think, in graph theory. And since October, he's a postdoc in our group. He will tell us about some scary hyperbolic things today as well. The floor is yours.
Hope I have time to talk about hyperbole, but it's more at the end. But yeah, I'll talk about infinite graphs, and infinite groups too. But okay, before this, I start with easier stuff. So thanks for the introduction, and I'm super glad to present you this work. So this is a work we did together with Louis. So Louis Esperet was my former advisor, but this work was done after my PhD. And also with Harmander Galavat. So Harmander was a postdoc in Grenoble, but now he's working, he started a new postdoc recently in Clermont-Ferrand, in Limos. And we started this work whenever we were all the three in Grenoble still. And so yes, so part of our results, so this is quite a new thing. It appeared on arXiv less than 1 month ago. And there was no other papers that appeared on arXiv, okay, with a lot of common results. So part of our results, they were found independently by Raphael Appenzeller and Kevin Klinger. The interesting thing is that they come more from group theory, geometric group theory. So our approach and our motivation for this result, they are quite different. So these are quite of complementary work, even though we have a lot of intersection on our results. And yes, so what I'll talk about is some variants, so some coarse variants of the traditional cops and robber games in graphs. So it will be in infinite graphs, okay? And yes, so this variant, they were introduced quite recently by Lee, Martínez-Pedroza and Rodríguez-Quinche. And my goal today, my main goal, it will be to show that these variants, so the parameters they defined, these cops and robber games, they are quite relevant. They fit very well, in fact, in the new, when we compare it to the new theory that just emerged a couple of years ago, let's say, on coarse graph theory, okay? And so they are really, so first time you see it, so I wait a little bit before showing you the definition, because the definition is not super natural first time you see this definition of these parameters. But in fact, it appears, even so, if they have well definition, to fit quite well in this whole, this overall coarse graph theory stuff. Okay, so let's start as warm-up with the usual coarse and robber game. Okay, so the traditional coarse and robber game, cops and robber game. So it's played on finite graphs. Okay, so you might be already familiar with it. So we are given a finite graph, G. Okay, base graph. So here I draw one. It was introduced by Kilio and Nowakowski and Winkler independently. And so you have two players who plays one against the other. So we have a cop player who plays with a certain number K of cops. Okay, so he can place them initially, give them initial positions, so position of vertices in the graph. And you have a robber player. And the robber player, we place with only one robber, right? So he places robber at some other vertex initially, once he knows the initial position of the cops. And at each round, the cops, so the goal, it will be ultimately to be able to win, to catch the robber, right? To capture the robber. And the goal of the robber, it will be to evade the cops, okay, forever. And so at each round, the cops, what they can do is that they are placed each on some vertex, they can choose some adjacent vertices, and they can either stay wherever they want, or they can move to some other positions, right? Like this. So here's the first possible move. Then the robber, so it's full information game, and all the variants we will see later, it's full information. So the robber knows where the cops are, he knows the whole graph, and reciprocally, okay? The cops also know the position of robber. And so next step, the robber saw wherever they moved, so he can choose one of his neighbors or stay wherever where he is also. It's another option. So here he can move, it's a possible move. Then we keep going on, okay, we keep moving, and we can see that in this execution of the game, so at some point, so the cops, they can occupy, in fact, some dominating set of my graph of size 2. So it means that whatever the next move of my robber will be, he will be adjacent to at least one of my two cops, so he will lose, so he will be caught at the next round, right? And so what I call the cop number of a graph, of a given graph, it's the minimum number of cops which is needed in order to always win, to always catch a robber in some graph. Okay, so this is for finite graphs. This is well-known parameter. This is not the one we will talk about. This is just a small warm-up, right? And so you can see that, so yeah, on the previous graph, so this cop number is exactly 2, right? With 2 cops In fact, you can always catch a robber by just going to this dominating set of size 2. It's quite easy to see, right? And we can see that 1 is not enough. I think it's not enough in this example, okay, to catch a robber. And okay, there are some notions, because the game we will talk about, it's not a game of capture. It's not a game of capture evasion game. And it doesn't make really any sense in infinite graphs. We will see why. But there's some notion which is quite important in the game we will see, and it's the notion that appears a lot in this initial game. It's the notion of guardability. So what does it mean, guardability? So in this thing, whenever you want to find upper bounds on the cop number of finite graph, a usual strategy is to fix a subgraph, okay, H, and to try to guard it. So guard it means I have my fixed subgraph H, and I will say that a collection of cops, they can guard it if they can find a strategy such that from some point, from some step, my robber will never be able, if he doesn't want to be caught by my cops, he will never be able to occupy any position in this subgraph, right? Okay, and so one of the first guardability results which is known from Egner and from is that, for example, if you take any finite graph, if you fix a shortest path, right, in your finite graph, one cop, you take any cop that you want, and you will be able to guard this path. So after some point, shortest path means I have a graph G, my ground graph, right, this black graph, and you take two people, and shortest path is just a path of shortest length between these two guys. So if I take these two people, they are not connected by an edge, but this is the shortest path.
And you take any two vertices?
I take any two vertices. I fix a shortest path between them. And in fact, with one cop, there is this nice lemma. It's not very hard to prove, but there's a little bit of work, right? And with one cop, in fact, I can ensure that after some step, I can find a strategy. If I give one cop and I give him this path, so that after some point of time, the robber will never be able to enter, to occupy some vertex of this path, right? Okay, and a consequence of this, so this kind of guardability result, so this result we don't really care for what follows. It's more that this guardability notion that I care about, because the game that I will present, it's really based on some guardability notion, right? Not on some pursuit evasion notion, on some guardability idea. And just, yeah, this kind of guardability results, they occupy quite a big role. So they allow, for example, so just this result, corollary, not immediate, but with some work, you can show that, for example, if you know this result, you can show that 3 cops, they are always enough to guard any, to win in any planar graph, right? So the cop number of any finite planar graph is at most 3. And okay, let's a little bit forget this notion of guardability, just keep the notion of there is some subgraph, and the goal of the cops, it can be to guard, right? So after some point, they don't want the robber to enter into this subgraph anymore. This is the only thing I want to remember about finite graph now, okay? Okay, and so the natural question now, when we see this, at least for me, the natural question is how can we define an interesting cops and robber game in infinite graph? Okay, now what when we consider infinite graph? Okay, so maybe the first question you have is why would it be interesting? And I hope that you will find some answer in this talk. But once you have this, okay, how to define it? And the thing I was claiming until now is that, okay, maybe you can think there exists some pursuit evasion variants of the cops and robber game, right? Where the goal of the cops is still to catch the robber. But what I'm claiming is that, okay, these variants, so they were studied in particular by Moir. I mean, it's Boyan Moir who introduced them a couple of years ago. But the point is that if you want this variant to make sense, at least in graph, you need at each step of time to have some non-uniform speed. So the speeds, so you have speed, which is the number of edges at each step that the cops and the robber can take. And you need them to be arbitrarily small. Otherwise, you can't really say anything interesting. And why can't you say anything interesting? For example, if all your cops and all your robber, they can just move by one step at each time. If you have just in an infinite graph, an infinite shortest path, right? An infinite geodesic. Once the cops, they have some position, the robber, he can just go far away from them, and then he will escape them forever, right? So at the moment you have an infinite shortest path, in fact, pursuit evasion games, I mean, at least me, I don't know any interesting notion of pursuit evasion game with uniform speeds, whenever everyone moves at the same speed at each round, right? In fact, the nicest, I mean, at least the version of the cops and robber game, which will make sense for us today, and which we will focus on, it's some version now where the goal is, as I said before, not to catch robber, but to guard something. And what we will guard is some ball. So now I will explain what it is. So definition is slightly technical. And it was some variant, which is some coarse variant. So I will see later what it means, coarse, and why we can call this game course. And it was introduced by Lee, Martínez-Pedroza, and Rodríguez-Quinche. Okay, so let's see this definition. So I put some memo here because we will need, in order to make sense, right? Just to memorize all the variants and all the parameters. But let's fix as before. So before we started from a finite graph, now let's fix an infinite graph, right? So this is our ground graph, the graph we will work on, right? We don't move this graph, we don't treat the graph, we fix an infinite graph, okay? And now we will, as before, we'll play with k-cops, okay? We have k-poks, and I teach step, they will occupy some different vertices like before, and we have one robber yet, okay? And this robber doesn't have to be caught by the cops, but it's not his unique goal, he has other goals. And now, at first, so then I will explain how we choose all these parameters. There is a bunch of parameters, right? And we will see later how to choose them, but first assume that we fixed a number of parameters. So these are the ones that I wrote at the top left. Okay, so the parameter of the cops, I put them in red every time, and the parameter of the robber in blue, to hope it helps a little bit. And so you have four parameters of interest. First one is the speed, the cop speed. So now our cops, they have some speed. What's the speed? So this is this SC. It means that at each of their rounds, they will not only take one edge, they can move using at most SC edge. Okay? So they can take any path of length at most SC. So this is a parameter, the speed of the cop. And you also have similarly a speed of a robber, which is the number of edge he can take to move at each of its robber round, right? And then you also have a new parameter, which is the reach. Okay, so the reach now, it's if the cops want to capture the robber, they don't have necessarily to be at the same vertex as him. They can just be at distance at most reach. So we have this row parameter, and whenever some cop is at distance at most row from the robber at some point of the game, he count it, and the robber immediately loses, right? So we have this new thing. So you can think about it as the cops, they have a lasso now, right? And they catch him from far away. And there's the last thing. So this thing, I put it in green because it's kind of neutral. It's a ball. Okay, so it's a ball of finite radius. So we are into infinite graph, but we have a ball of finite radius, right? And this ball is a ball that my cops, they have to guard, and that my robber, his goal will be to enter into this ball an infinite number of times, right? Hope it's clear. Please, this is a best moment to ask questions, right? If you have questions, don't hesitate. I prefer to spend time on these slides and on the next one, because this is a thing we'll consider from now on. And so now now we fixed all these parameters. The game is as before. One execution of the game is like this. So as first steps, my cops, they will choose some initial positions, right? Once they have their position, so again, it's full information game. So the robber knows this position, he knows the whole graph. He can choose this position. So he has to choose a position, initial position, if he doesn't want to be caught, which is at distance more than the reach of the cop, right? Otherwise, he immediately loses. So he chooses another position. You have this big ball, right? And at each step, so the cops, now they can move, right? And if during their move, at some step of their moves, so they move, they are constrained by the speed SC. And if at some step of their move, they are at reach, they catch the robber with the lasso, then the robber loses. Okay. Otherwise, if they couldn't catch him, then he can move, and he can move using a path of length at most speed. And then we keep going on. And now his goal is not only to evade the cops. His goal is that you have this big ball. I didn't explain yet how to fix all these parameters, but you have this big ball, and his goal is just to spend an infinite number of steps in this ball. Okay. Or if you want to state it otherwise, the goal of the cops is to guarantee that after some point, either they catch the robber, either after some step of time, the robber will never enter in the ball anymore. Okay? Okay, and so now, how do we fix the parameters? It's the only thing I didn't...
So I can try to interrupt. So in the setup, I should think that the speed of the cops is larger than the speed of the robber. So I should think about that.
Yeah.
So which means that basically in no point of the game, the distance cannot be finite between them, right? Because once it's finite, you can just
No, it will be finite, but not bounded. Like if the distance is less than the speed of the cop.
Yes, you said it right.
So the cop move, but right after the robber moves. So he can still keep some distance between them. So usually, you're right. We will see it later, but usually we may always assume that this speed of the robber is at least the one of the cops. This we can always assume.
At least or at most?
at least. The rubber is yeah. So, but yeah, okay. Maybe it's what you had in mind. If your graph is finite, or if your graph has finite diameter, you can fill it with copes, right? Or you can just fill it with one cop with a reach, which is the radius of the graph, and then just the rubber cannot even start to play without being caught. So this game, we will see that it makes sense really for infinite graph, or graphs with infinite diameter, in fact.
Okay. They move alternatively, yes?
They move alternatively, right? First cop, and then rubber. Exactly. Always. First cops, then rubber. First cop, rubber. Exactly like before, right? It's exactly the same order of steps. So the only thing I didn't explain yet is how to choose all this speed, reach, and everything, right? And there are two ways to choose it. And so here I put some memo.
Can we stop for a moment? You said that it only makes sense for infinite diameter.
Yeah. I didn't explain how you choose, in fact, the thing, but in your mind you can assume that all these parameters, they might be arbitrarily larger than any given constant that okay. It will make sense after I show you the game, because I didn't explain you how to choose the parameters. So maybe let me explain.
Once the parameters are fixed.
Oh, once the parameter is fixed, it's not the same story.
The graph is not really infinite anymore, right?
Okay, I agree with you, but the point is that the graph is fixed and then the parameters are fixed. So that this way, which will make it. But there are some interesting questions on finite graph too, which are hidden behind. I don't know if I will have time to talk about them today, but there's definitely some interesting stuff to say also about this. If we fix first the parameter and then the graph. We have some questions, but I don't know if I will mention it. Okay, so yeah, so once I fixed all my parameters, so here I put some radius, okay, you can replace it by ball. We will see that it's more or less equivalent, okay, the radius, so just assume that we are targeting, the rubber is targeting some ball of finite radius, right? And I say that my graph, once I fix all these parameters, it's cop-win whenever my k-cop, they can always protect any ball in my graph of radius r, right? So this is this cop-win, just if I fix everything, my cop, they can always protect any balls that I of given radius. And now you have these two games. Okay, here are how these two games are played. So first we have this graph, which is fixed, known by everyone, right? By both players. And you have first the weak game. So the weak game is harder. You have to think it's harder for the cops and easier for the rubber. Okay. So in the weak game, the first step is first my cops, they choose both their parameters, both their speed and their reach, right? So this is I put some memo here because we won't have these slides anymore later. So first step is cops choose everything, and then once he knows everything, the rover now he can choose his speed. So this speed can be any function of the speed of the cops and of the speed of the rover, of the reach, I mean. And he also chooses R, the radius of the ball he wants to enter in. Okay, so this is a weak version, and then they start playing the game that we saw before, right? But this is a weak version. So first we choose cops choose all their parameters, and once they know their parameters, the rover can choose his speed and the ball he wants to play with. But we'll see some examples.
Can he always take something super massive?
Yeah,
So that he can
always, but finite. Still it's finite.
Yeah?
Still it's finite. He doesn't have infinite speed. That's the only restriction.
So his parameters are another what you are.
Yeah.
Okay.
There is still some fixed graph you have to remember, right? And we'll see that he's not as powerful as we think he is. I mean, he is powerful in many cases, but not always.
He also chooses V0, right?
And yeah, okay, so that's the next slide. So we will always assume that G is connected. In fact, when the graph is connected, choosing the radius or choosing V0 is the same thing. Okay, so in fact, this you can replace it by, we will always assume that our graph is connected, and we can replace it by it chooses ball. You just choose a ball, but a ball of finite radius, right? Okay. So I say again in this weak version. So you have first step, the cops they choose their speed and their reach, and then once he knows all of this, my rover he chooses his speed, whatever function he wants of the speed of the cops and of the reach, and then he chooses a ball he wants to play with, right? The ball he wants to enter infinitely often. Okay. And the strong game is slightly more restrictive for the rover because so it's still the cops have to choose their speed first, but now right after the rover he has to announce is there's some echo.
Oh, it's me.
And yes, right after he knows the speed of the cops, he has to decide and to announce his speed. Okay, the robber. And now, after this, the cops, they can adapt the reach. So now the reach of the cop, it seems a little bit artificial. We will see why it's different notion and what the cops, they really do have more power in this version than in this one. But once they know the speed of the robber, now they can choose the reach. And once he knows everything, now he can choose the ball, in which he is a ball of finite radius. Still, this is the only constraint, but in which he wants to play. Okay? Okay, and these two games, these two different games, so here's the memo there, they define two parameters, as before. We had the cop numbers, now we have two different cop numbers.
There was a question about V0, I didn't hear the answer. Who chooses V0?
We may assume that the robber chooses V0. We will assume for now.
After all, or
yeah, so in fact, here in this slide, the V0 is hidden in this scope wing condition that I wrote. So here it's how it's written in all the paper, but let's say that you can replace this R by B. Okay, so the robber chooses the ball.
Okay.
Let's say it, right? But the only constraint is that the ball has finite radius. It's not the entire graph. Okay? Otherwise, it's too easy for him. He just have to evade. So there is some... I was about to give some examples later, but maybe I can just give some pictures. So you have this ball, B, right? And you may assume, so in terms of scaling orders, you have first, so you have these cops, they announce their speed, okay? And their speed, they will be ridiculously small compared to the radius of the ball, because the ball, it's what is chosen at the very end.
yes.
And so you have this speed of the cop, right? And you have this speed of the robber. He can always choose it far larger than the speed of the cop, you can see, because he always chooses it after the speed of the cop, right?
Yes.
And you also have the radius of capture. So whenever there are some position, there is some ball of radius rho that my cop, okay, this is or that my robber has to avoid, right? And in the weak game, we can think about this small rho disk as being very small, super small, because he can choose his speed right after, right? But in the strong game, this rho then can be super big, this radius of capture, compared to his speed, right? Because they can choose it afterwards. And that will change some stuff in the game, we will see it. Yeah.
And I still don't understand, what does it mean for this weak cop number? K cops win the weak game. It means that, I mean, maybe I'm still not understanding, but in the weak game, for any number of cops, once they choose SC and ROM, can't the robber choose something so massive?
Actually, think of a two-ended graph.
Eh?
Think of a two-ended graph. A two-ended tree. One cop wins. One cop wins on a two-ended tree.
Yeah, so on trees, the cop will always... Okay, maybe we can...
The robber can jump 100 positions.
Okay, so the goal, there is a ball. There is a fixed ball, this green ball, right? It's fixed somewhere. It's hidden in the graph, right?
Yes.
And this has finite radius. And the goal of the robber, it's not only to avoid the cops. So you have these cops. These cops, they move. They all have their small disk, but it's only the small disk that they are guarding. So these are disks of this radius, rho, right? And the goal of the robber is to avoid them. So he can avoid them by taking some paths, but this path, they have some length, which is determined by this parameter SR. And his goal is to enter and spend an infinite number of time in this ball. So maybe sometimes he will be chased, but then if he's chased, he has to come back at some point, okay? And the goal of the cops is they have to block him, to stop him, to find a strategy to...
But can he go through the cop's balls?
No, he cannot. Sorry, I didn't precise. Okay.
He
Okay,
has
sorry.
to take a path.
No, I completely miss it. He cannot jump. He cannot jump.
Ah.
I got you. Okay, I'm super sorry. I completely forgot to precise it. I don't even know if I wrote it, in fact. But he cannot go. Okay, yes, I explained everything. So yes, so if the cops doesn't move, he cannot go through them.
Okay, then in a line, one cop was okay.
Okay, sorry. So yes, so in a line. Okay, so let's start with an example. We will come back to this later. Okay, take a tree. In a tree,
Yes.
even if it has infinite degree,
Yes.
one cop will always win. And he will win both games, the weak and the strong, right?
Yes.
Because every ball, it has finite radius, right? The cop, he can do what? He will do something super stupid. He will start at the center. He can even take a reach equal 1. He doesn't care, right? Takes reach equal 1, speed equal 1. He doesn't care. He starts at the center of the ball. And then the robber is somewhere, and will just go going closer, closer. And the robber, he cannot jump, right? So at some point, he will just kick out of the ball, and he won't be able to enter anymore. And the cops, he will just stay there, and it's fine. Okay? So the cop numbers of the tree is 1. All trees. Okay? I hope it's okay. Sorry. Thanks a lot for this question. That's important. That's an important point. Okay. So yes. So this is what a question of Grzegorz. We may assume the center doesn't matter of the ball. We may assume that the robber, in connected graph at least, the robber, we may always assume that he's choosing the whole ball, right? And yeah, I didn't explain, I think, what this weak cop and strong cop number are, but I think you can guess what it is. So as before, it's the minimum number of cops which is needed to have a winning strategy, but the point is that it's infinite, so maybe sometimes finite thing doesn't matter, so it's not really minimum, it's infimum, in fact. So these numbers, they might be infinite, okay? And so if you have some cop numbers, so the weak cop number, for example, which is infinite, it means that no matter the case that you have, finite number of cops, they will never be enough to win against a robber. So yeah, I told you, first time you see the definition, it seems quite artificial. Now my goal, it will be to convince you that in fact it's a good notion when you do a coarse graph theory. Okay, I hope that you will be convinced after that. And yes, so I told you in the strong game, the cops is more powerful, and so it just translates to this inequality. So maybe I can write it also there in order not to forget about this. So it's this direction it goes. And it's not true in general, we'll see some example. But this is always, okay? So it just expresses that the cops has more power in the strong version of it. Okay. So now, yeah, I'm telling this is coarse variant, coarse from the start. So, okay, maybe let's talk a little bit about coarse. Let's explain what it means. So there is this coarse geometry branch, which appeared, let's say, maybe a little bit with Gromov, okay? And now there is this new coarse graph theory domain that emerged more recently, but which combines both modern and old stuff, okay? And in coarse stuff, so in coarse geometry, let's say, what we are interested in we look at graphs or we look at metric space, but from far away. We don't don't care, in fact, about what is happening locally, right? We just look at them from far away and we look at their global structure, right? So up to rescaling, in fact. And so it means, if we want to precise it, to formalize it, means that we look at a graph, so infinite graph, let's say, up to quasi-isometry. So what's quasi-isometry? So I will say that two graphs, they are quasi-isometric to each other if when I look from far away, they look the same. And so it means that formally, I can find a mapping from the first to the second, so from H to G here, okay? So it's mapping vertices to vertices. And there exists some constants, so these are distortion constants, let's say. And first condition is that, okay, the distance in my graph G, they are more or less the same, up to some constant multiplicative and additive distortion. They are more or less the same than in my input graph, right, in my initial graph H. So if I had two graphs which were at small distance in H, they will be sent to two vertices which are at small distance, up to this deformation, this constant deformation. And if I had two people that were far away from each other, then they are sent to two people that are still far away, up to some multiplicative and additive constant, okay? And, okay, quasi-isometry, it's an equivalence relation. So if I just have this first condition, it's not enough to make it an equivalence relation. And I need, in quasi-isometry, to have this second condition, which is called quasi-surjectivity. Let's call it quasi-surjectivity. So I say that I'm quasi-isometric, so I'm quasi-surjective. If moreover, so I have this mapping so it's from H to G, right? If moreover, so maybe I have my image here, f of H, right? In my graph G. And there are some people that might not be in my image, but then in this case, it means that they are at distance, at bounded distance from my image, at constant distance. So this bound is this constancy, okay? And these two things, so it's some exercise that you can try, it defines an equivalence relation. And now if I just have this first condition, so it doesn't define an equivalence relation, so if I just drop this quasi-surjectivity thing, if I only keep one, so this function f, I will call it just a quasi-isometric embedding. Okay, I will say that my first graph H is quasi-isometrically embedded into my second graph G. Okay, so in particular, if we have two spaces which are quasi-isometric to each other, you have quasi-isometry from the first to the second, and from the second to the first. Okay. Okay, so here's a small example. So you take the infinite graph, or any graph, you subdivide a constant number of time, but bounded number of time every edge. You add some small stuff, you do some just local modification, and the whole thing that you obtain, in fact, if you look from far away, you didn't make any real big change, okay? It didn't have a wall impact. But if you add a new universal vertex now, on infinite graph, now it will change a lot of things, okay? So this won't be a quasi-isometry. Okay, and so yeah, and usually, so in coarse geometry, and we'll see a little bit why, some motivation about it, we are very interested about the properties which are preserved undertaking this kind of equivalence, okay? And so surprise, so why are these games coarse? Why do I call them coarse variants? So in fact, whenever you take two graphs which are quasi-isometric, one to each other, so in fact, they have the same weak and strong cop number, okay? So these are quasi-isometric invariants. So quasi-isometric invariant, we also can call them in the literature geometric invariant. So this doesn't change up to quasi-isometry. And so this was in the first paper from Martínez-Pedroza and Rodríguez-Quinche. So this is already a good reason to just work on this parameter. Okay, there are other good reasons that I will show. And what we show, so our first thing, so it was answering, in fact, in the positive way, some question of the initial paper. It's some strengthening of this result is that now if we just take, if we remove this quasi-surjectivity assumption, so if we just take a quasi-isometric embedding of a first infinite graph to a second one, in fact, we have some monotonicity of this parameter, right? So this is stronger because when I told you, when you have quasi-isometric embedding, you have, when you have a quasi-isometry, you have quasi-isometric embeddings in both directions. Okay, so I don't want to spend too much time on this. So this, I won't have time. It's quite technical or proof. I mean, there are a lot of tricks that we have to add. But this, I will try to at least give you the idea of this first result because it will help just to understand a little bit these parameters and quasi-isometries. And so, yeah, so I will not give a real proof with all the nice constant and everything. I will just give you the rough idea, okay? The coarse idea, let's say. And so I assume that I have two people, H and G, okay? And I fix some quasi-isometry from H to G, okay? So this sends my graph H.
My graph is isometric, quasi-isometric to a tree, then it's 1.
Yeah, exactly. We saw that trees, they have 1. So if I'm quasi-isometric to a tree, my weak cop number and my strong cop number, they will have, they will be 1. And in fact, we have. Okay, I won't spoil it. We'll see later some more good news about this. Okay, so assume. So what I want to say is, okay, assume that I have a quasi-isometry F. So some mapping from H to G. Okay, and so this is quasi-isometry. So here, everyone in G which is not in my image, it's at bounded distance, right? So there was this C constant, remember, in the definition. So assume that you have such a thing, and what I want to show is that, okay, if my robber in H, he can win against K cop in H, okay? So if I have weak cop or strong cop, we don't care, it will work the same, these two proofs, of H which is strictly greater than K, then I want to show that it implies that the same thing on G is strictly greater than K, okay? That's what I want. And in fact, it will be enough, because if I'm quasi-isometric, I have these things F in both directions. And what I would just want to convince you that, okay, this statement is true, and this will imply this first theorem, okay? And what will be the thing? So assume that we are a robber, we are playing against K cop, okay? So there are cops somewhere there, okay, placed, and they have some parameter. Okay, so cops, let's keep my color code, let's denote them in red, okay? So they have some reach, they have some speed, and okay, we will take the speed, let's say twice. Okay. I didn't explain how we choose our speed yet, but it doesn't really matter. Just the idea of the thing is that, okay, my cops in my game at each point, either they will occupy something which is in f of h, but this f of h reminds that it really is super similar to h, okay, up to quasi-isometry. So in which case, if I have a cop here, Ci, which occupies some vertex here in f of h, I will create a virtual cop with some parameters. So this parameter I didn't explain how, but they are related up to the constant which are hidden between this f to the parameters, so the speed and reach in this graph, okay? I can create some virtual cop. Okay, so they are virtual; they don't really exist in my initial graph H. And whenever I'm not in the image, in fact, you know that because of quasi-isometry, I'm still not far away. So if I'm not in the image f of H, I know that still if I look at the people which are the closest to me in this graph H, they have bounded radius, okay, and bounded up to this constant, this C, okay, and up to the parameter of my graph. So in fact, whenever I have a graph here which is not in my image FH, still I can map it. Again, I take any one here, okay, and I map it to another virtual position here in H, okay, which is the virtual position of anyone which is at closer distance from me, okay. And what I'm pretending now is that here in this graph, I assume that I can win always against k-cops, okay, as a robber. And so what I will say, what I will do is that I will just reproduce the strategy, the winning strategy here, up to this rescaling factor. So I don't want to give any constant there, okay? But up to this rescaling constant that there is, I will just say that, okay, I have a winning strategy here, and now when they move up to this constant, they will move like, it will be a restrained move, right? And so I will have some moves, and whenever in my winning strategy it tells me to my robber to go there, then I will go there in this image. And this is more or less just the intuition about why this first theorem holds, okay? And this is very coarse reasoning. So really, it's just some rough intuition, okay? And okay, the main difficulty maybe, just the only thing to say, why it's not enough to prove this result. So now just the monotonicity when we don't have quasi-surjectivity, because now, if we have cops, we are playing there, and if we have cops which are arbitrarily far away, okay, from this image, if we look at their projection, we cannot assume that they are anyone here, because they are far away, and we cannot really have a real candidate about how to represent them in H. And so here for this, we really need some more tricks, some silly tricks, okay? It's not that much complicated, but it's quite technical, okay, to make this idea works. So yes, so there is more thing in this second thing. Okay, so that was just a rough idea. Okay, I already talked a lot. I still have a lot of things to say. Okay, so is that clear? Actually, the statement? Okay. Now, yes. So I wanted to do a small parenthesis on about groups, and so there are two reasons for this. So the first one is that groups are the main motivation to study quasi-isometry, and I will just give you a short argument for this. And second motivation is that so all the results that we get for graphs, we can derive some interesting stuff about groups. And in fact, the original motivation of looking at these parameters was to study cop numbers like cop games on groups. Okay, so let's take a group. So let's do this small parenthesis. Let's take a group, okay? So my group, it might be infinite, so I will denote it with this gamma, but it will always be, I will always assume that it's finitely generated. So it means that there always exists a finite subset of generator on my group, okay? So we denote it S. So whenever I have a pair like this, okay, so some group, some finite set of generators, can define what I call the Cayley graph, okay, of the associate pair, so of gamma with respect to S. And it's a graph in which I will put, so it will be infinite, whenever my group is infinite. And I will put, okay, one vertex for each group element. My vertex set is gamma. And around each vertex, I will do exactly the same. So I'm defining an oriented arc, but when I, an oriented graph, but when I talk about Cayley graph, I just mean I'm working on the undirected graph, which is hidden behind, okay? The undirected version. And so around every vertex now, so remember a vertex is a group element X. For every people in my generating set, I will add an arc going from X to the element I obtained by multiplying X by A on the right, let's say, okay? So here for Z2, for example, if I take this canonical generating set, if I do this around everyone, the graph I will obtain, the Cayley graph, it will be the infinite square wave, right? An important thing is that, okay, this definition of Cayley graph, it was really dependent on this finite generating set, right? Remember? So if I add some useless generators here, for example, I obtain this Cayley graph for the same group, right? And it's not planar anymore, it's not the same kind of graph. And now the big question is how, okay, I think you see it coming from far away, how are two Cayley graphs of the same group related? So what does it mean to change generating sets? So if I have two different generating sets but finite still for the same group, in fact, when I go from S to S prime, it's exactly the same as taking a group element. So okay, I take an arc, it corresponds to one of my generators. In fact, I can express it in my second basis, right? In my second generating set. In fact, what I do when I go from one Cayley graph to the other one, It's exactly, I take every arc and I replace it by a path, and this path, they always have bounded lengths. Bounded because both of these things, they are finite, okay? And so I think you saw it coming, but okay, restate it. So this very simple observation, it allows to say that in fact, if I fix a group to generating set, any two Cayley graphs, they are related by quasi-isometry, okay? They are quasi-isometric always. And that's why, that may be the first reason I think why we do care about quasi-isometry. It's because so whenever you have a property, like the weak Cope number, the strong Cope number, which is preserved under taking quasi-isometry, then you can define it also at the level of group, right? It becomes a group invariant, Cayley graph invariant, okay? And so in particular, that's what I will do now. I will talk about the weak or strong Cope number of a group, okay?
This statement makes all the sense for infinite.
Yeah. You have every finite group or quasi-isometric to each other. They are all quasi-isometric to a trivial group, to a point.
But then your groups are still finitely generated always.
Yeah, always. Yeah, if you remove this finitely generated stuff, you don't have this bound on the size of the path. So there might be some way maybe to patch it in some special case, but I don't know. Let's just talk about finitely generated stuff, okay? Okay, so recall that for trees. Okay, so now, I don't know, how much time do I have?
Fine.
Okay, I guess. Okay, so let's forget a little bit of groups. We'll see later. We'll see them again later. Okay, so we saw that for trees we have both our Cope numbers which are equal to 1, right? And so, okay, the first thing, at least from a graph theorist approach, if you want to find upper bounds, the first condition, natural condition that you want to say is, okay, do we still have the same reasoning which works whenever we work on graphs with finite treewidths? Okay, so if I take an infinite graph, G, of finite treewidth T, can I bound its Cope numbers, so its weak and strong Cope numbers? So usually it's something that we can do with usual Cope numbers, right? And the thing is that, okay, still it's the case, but it's the case only when we focus on graphs which are locally finite. Okay, what does locally finite means? So an infinite graph, it's locally finite whenever all vertices, they do have finite degree, okay? So there is no vertex of infinite degree. And we'll see that this statement, so this is not a hard proof, we can see quickly how it works. It's exactly the way that you want it to work, that it works, okay? But you need this locally finite assumption to make it work, okay? And there are examples with vertices of infinite degree which makes this kind of statements fail, okay? So if I take a graph, assume that it has treewidth T, and take a tree decomposition, okay, of width T, so each bag has length at most T plus 1, and what I'm claiming is that if my initial graph was locally finite, T plus 1 copes, they are enough to win, okay, in my variance. So in my weak variant in particular. So because of this inequality, just showing it in the weak variant, it's enough. And the strategy is super easy. So at the first step, my copes, we don't care about the reach, about the speed. We just put them to 1, okay? We don't really care. Assume that my robot shows some ball. And we just choose one bag. We occupy all the vertices of this bag. Okay, we assume that my graph is connected also, otherwise it doesn't work anymore. And now, because of I'm a tree decomposition, my rubber is only, like it cannot, its position cannot intersect, whatever it is, it cannot intersect two different connected components of my tree minus the node that I'm occupying, right? So it's really like we know where to find it, right? If you want to catch him or at least to chase him. So we'll chase him, it's exactly like in finite graph, right? We do this with respect to this tree, decomposition tree. And so we will move, so they're all these people, so we look at the neighborhood. So you have T prime, which is the vertex in T2, right? The neighbor of T in T2, and T2 is a connected component of T minus T, small t, which contains my rubber, right? In which my rubber is located. And so everyone who is in the intersection, so this intersection is a separating set in my graph between bags in T1 and bags in T2 only, okay? And now all the other which are not here, they can move to the symmetric difference, okay? So we can move like this, and it's exactly what we want to do in general in usual cops and rubber games. It's quite an easy strategy, right? And you can move like this, okay? And the rubber, because you occupy this whole intersection, it cannot jump, right? It cannot jump. That was our previous observation. So it cannot go to some occupy some vertices which were in some bag of T1 but not of T2.
But where did you use the assumption of locally
finiteness? The assumption is that, okay, even whenever it's not locally finite, I can still do this an infinite number of times, but the point is that maybe my ball contains, like it's spread amongst an infinite number of people here. So for example, take the grid and take just one universal vertex, and you see, or take any graph with a universal vertex, it will make it fine. It will make it fail. And so the locally finite assumption, it just means that after a finite number of steps, I will guarantee that now everyone, all my ball of finite radius that I want to protect is behind me. Okay, and I need locally finite I need my ball to be finite, in fact, to make it work. And so now it raises some interesting question. It raises the question of, okay, maybe is this definition of the good one? And there is an alternative definition that you can consider, these weak and strong parameters. And this is, instead of choosing now some ball of finite radius, you might want just to play in some finite ball. And now if we play with this version of the games, so now the robber, he can just play in a finite subgraph. It's a finite subgraph that we have to guard.
Just connected.
Yeah, connected usually. We can assume it. It doesn't harm. It's not. I mean, it's harmless. But now, if we just want to guard or to enter, to penetrate infinitely many times in some finite balls instead of some ball of finite radius, now this will work, and we can remove this locally finite assumption. Okay. In fact, these parameters, we think that we're playing with finite balls, so it's just a small detail. Like both notions, they are the same. Both parameters we define, they are the same in locally finite and non-locally finite graphs. But when we have vertices of infinite degree, in fact, we think that this version of the game is more interesting because it's the one that really captures, like, we don't need these additional parameters. And everything works the same, all our proofs work the same. Everything that I will present now, it also holds whenever you replace this condition, like you look at this slightly modified version of the games. But that was a side remark, okay? Thanks for the question. Okay, so that's more or less clear. So whenever we look like a tree, so in the graph sense, so whenever we are quasi-isometric, let's say, or just whenever we have bounded treewidth, or quasi-isometric to some guy of bounded treewidth, we have a finite cup number, and the bound is a weak cup number, and the bound is the following. Okay, so first observation is that this bound is tight, so maybe I'll skip the example because it's not the most interesting one. But yeah, okay, there's a simple example to see that, in fact, we cannot hope to improve this bound. So when t equals 1, okay, this is 1, this is not optimal, but whenever we look at graphs with treewidth 2, there is this example when you take this graph and this I subdivided copy and you glue them together on an infinite path, right, just to make the whole graph connected. And this shows that you cannot improve this upper bound, right? So I won't explain why. And there is this example, which is slightly more interesting. And this example, it shows that this locally finite assumption, it cannot be dropped. So in particular here, it's a graph with one vertex of infinite degree. All the others, they have finite degree. And it has treewidth 2. So I will explain what this graph is, because this one is more interesting. It has treewidth 2 because there is this universal vertex. If I remove it, what I obtain is a forest. But it has weak cup number infinity. And I will try to explain you what this graph is, because it was not obvious for us at first, this example. It took some time before realizing that it was existing, this guy. So take, for any d, okay, greater than 1, take the TD. So TD is the d infinite regular tree, okay? So it's a tree of degree d, okay?
So it's like infinite also upwards, right?
And I didn't explain yet, so that's the first step of the construction. Now, to this TD, I attach some universal vertex. Okay, I will call it ZD. And I attach it to all the nodes of my tree, okay, like this. So it sees everyone, so it has infinite degree in particular, right, this guy. And now, this graph that I obtain, I subdivide it with this additional universal vertex. I subdivided each edge d times, okay, or d plus 1 times. We don't really care here. Subdivide. So this gives a graph which I'll call GD. And now the graph G that I wrote here, it's exactly the graph that you obtain whenever you put, okay, you have this Z1, Z2, and so on, and you put, so all of these GD copies next to the other, and you glue these ZD vertices together, okay, into this big vertex that I call Z, okay. So you have this Z there, which is universal with every edge divided D time to each TD, okay, each tree like this. So this D regular tree, this subdivision, D subdivision of the D regular tree, and you do it like this, okay, with one guy like this for every value. So TD plus 1 and so on, okay. And my claim is that, okay, first this graph G, so it's the one which is pictured there, partially pictured. It has treewidth too, okay? If I remove Z, I obtain a forest. Okay, the only cycle that I have, they go through Z, okay? And second observation, which is more interesting, is that it has infinite weak cop number, still. And why does it have infinite weak cop number? So in fact, you can play, so whenever, okay, you're the robber, you wait the cops to choose their parameters, so they will choose some speed, some reach, okay? And once they choose it, you will choose some D, and this D, you can choose it like greater than, let's say, from memory, I think this should work. And okay, let's just maybe put the number of cops, okay? So assume that there are K cops, you play with K cops, and you want to find a winning strategy for the robber, right? So this will be, this exactly means that the cop number is infinite, okay? It's infinite whenever you can win against any fixed number, finite number of cops. So fix a number K of cops, and wait them to choose their row, their reach and their speed, okay? And now, when they choose it, what you'll do as a robber, you will. I'm claiming that I can find a strategy to just remains into TD, okay? Into some copy of TD. And this copy of TD, the fun thing is that it's in some ball, and it's into some ball of radius, okay? If you want all subdivision of radius 2D around this thing, around this Z, okay? In fact, if I'm able to just win in the pursuit evasion game once we fixed all these parameters, and my speed, okay, my speed I can just take the same than the cops, it will work. And if I'm able to stay into some copy of TD for D large enough, and escaping my cops in this copy of TD, so this copy, it will be entirely included in my ball of finite radius, right, around Z, of radius 2D. And if I'm able to do this, then I'm able to win and to stay infinitely number of time, like all the time, in fact, in my ball. Okay, so I think there's something that I think quite badly because. This is a claim. I don't want to say more. I can say more if you want. Okay, I can. You want to explain why?
Yes. I want to see how he evades. Yeah.
Okay, so let's do it again. We fix this row, this, and this speed of the cop. Okay, and let's take just my speed. I don't care about row. In fact, let's just take the speed of my robber to be twice. This will be largely enough, right? Twice the speed of the cop. And now I'm taking a copy of my tree. So this tree, remember that they are subdivided D times, right? In the D time. And I'm claiming that I have a winning strategy to escape forever my cops, my K cops, they are K cops. And I chose something which is greater than K plus 1. That's stupid, but I chose something which is greater than K plus 1. So first thing is that I have K cops, okay, in this D subdivision. I'm in this tree like this, okay? And the thing is, okay, so let's place them somewhere. If I choose this D to be, okay, this D, I choose it so that whenever my cops are somewhere, so if they are at some edge which was subdivided, they can only be at reach, there is only at most one of these two vertices, which is at distance less than rho for any cop position. That's the first thing, okay, to see? So if I have some cop which is placed somewhere on this copy, or even in the whole graph, okay, which is placed somewhere on my whole graph, because I chose this D to be greater than 2 times the reach, wherever it is, there is only one position that I can occupy, right? One node of my initial tree, my tree TD, which was subdivided D times.
But the thing we don't see, I guess, is that the cop can be a decentral vertex.
Yeah, so
can be?
A cop in Z.
Okay, the cop can be in Z, but now it's the thing that I didn't explain yet, is that the cop is in Z, but this was also subdivided D times. So if he's in D, or if he's in another copy, it will take him some time before reaching some vertex. Okay, so if he's there, I don't care. So now what I'm doing, the strategy for Robert to escape the COP, is, okay, I project his COP, I look at which of all these vertices is the closer from the COP, okay? I project the COP toward this vertex, right? Yes. And now I'm just choosing another vertex as initial position, okay? I choose a vertex, and now I wait my COPs to move. And it takes them some time. It takes them at least 2 steps just to cross an entire blue edge, right? Because of this big choice of D. And so whenever they move, so if there was someone in Z, maybe it will appear at some point, but the time it will take just to appear there, I will already have some time to cross this thing, because okay, so sorry. I put this 2SC, but if we want even to be stronger, we can also put this D, just to be able, if I want as a robber, I have even the power to just cross the blue path in 1 step, right?
But then your D is dependent on
Oh yeah, okay, that's if I just want for the weak version, you're right. In the strong version, but in the strong version it will work also. In fact, same strategy will work if I forgot this, but it's just to see it in an easier way. Yeah, if I want.
It's important because there can be many cups in the central vertex, and they can together go, so you still need to have a degree. Right?
Yeah. And yeah, the degree is important. That's why I put it here. That's why I put the degree here. The degree is important because if my cup they project, I mean every cup it projects it's only closer to 1 vertex at most. And now if I'm somewhere, if my cups they surround me, there will always be an escape road. Okay, because of the degree. Okay, that's a fun example I find. That's a fine example, and it really shows quite well the limit of this kind of propositions. Okay, so sorry, there's still some stuff that I wanted to say, and I didn't even started. Okay, so now we saw techniques to upper bound the number. Okay, now what about lower bounds? And now maybe that's my favorite result. So a very great tool and very modern tool to find lower bounds on a COP number. It's called asymptotic minor. So asymptotic minor is something that have been introduced quite recently. So it's based on some older notion of minors, so which is this notion of DFAT minor, DFAT models, okay? And it's a metric generalization, okay, of the usual traditional notion of minor in graph theory, okay, in structural graph theory. It was introduced by many different people at the same moment. And this notion of asymptotic minor, which is a coarse version of it, it was introduced by Georgakopoulos and Papasoglou in this very famous paper with a lot of questions about coarse graph theory. And so this notion of asymptotic minor, they introduce it as a good candidate for a coarse analog of minor in coarse graph theory, what they call coarse graph theory. And okay, so here how to define it. So fix some finite graph H, okay? It will always be finite in what follows. So it also works if we take H to be infinite, but fix it to be finite, okay? And assume that I'm in an infinite graph G. I will say that I can find H as a DFAT minor, so I can find a DFAT model of H. If I can find, okay, so if I have this graph H, and for each vertex, I can find what I call a corresponding associated branching set in my graph G. So what it is, it's exactly in minor, it's a connected subgraph, okay, an associated connected subgraph of my graph G, such that every 2 branching sets first, they are at distance at least D from each other, okay? And then whenever I have some adjacency in H, so if I have an edge between 1 and 2, so between the corresponding 2 branching sets, there must exist some path, and this is also part of my model, so this part I will call it P12. And this path, it's internally disjoint from all the VIs, right? So it only intersects the VI in its endpoints, okay? The 2 people that you want to connect. And moreover, you also need to have 2 metric condition on it, so which is that this P12, it must be at distance first D from any other branching set than the one you're connecting, okay? So this one, which connects, for example, 1 and 2, it must be at distance D from V3, from V4, from V5, from V6, okay, and so on. And moreover, any 2 branching paths like this, they must also be pairwise at distance D, okay? So this is definition of DFAT minor, DFAT model, okay? And I will say that my graph H, I can find it as an asymptotic minor of G, so it only makes sense again for infinite graph, whenever G is an infinite graph, if for every D, now for arbitrarily large value of D, let's say, I can fit such dfat model of H. Okay. So is it fine with this definition? Okay, and this definition, it might be maybe the most important point of this paper of Georgakopoulos and Papasoglou. And okay, first, so okay, it's an exercise that you can try to do if you didn't saw this result before. That's the main motivation for considering this notion of minor, is that the first thing is that the property for fixed graph H to have it as an asymptotic minor, it's a quasi-isometric invariant, right? If I have two quasi-isometric graphs G and G prime, then my first have a copy of H as an asymptotic minor, if and only if my second has H as an asymptotic minor, okay? And so our result is the following. So now, about lower bounds. If I'm looking at the graph G, if I know that it has some finite graph H as asymptotic minor, then the treewidth of this graph H gives me a lower bound on my weak cop number on G, okay? So in other words, the weak cop number of a graph G, it's lower bounded by the supremum over the treewidth of all its finite asymptotic minors. Another way to state it, maybe less simple. Okay, so first observation is that this bound is tight. I mean, I don't have any better lower bound in terms of treewidth, okay, of my asymptotic minors. And this is an example which realizes it, so I won't spend time on it, but this is an example. So it says before, I just have some kt, okay, I fix some integer t, I take some kt, and I take this copy subdivided I time, right? And I'm claiming that this guy, it has a treewidth t minus 1, and this is exactly the weak cop number of the whole graph, okay? So there's no hope to improve this lower bound. And okay, why is this result, I think, quite interesting from a cost perspective? When we combine it with the previous proposition we have, it's because of this conjecture, in fact, of Georgakopoulos and Papasoglou. So this is quite this is very widely open conjecture, and this satire, it's very recent, but there are already a lot of people that already started to work on it, both from graph theory and geometric group theory. Okay. And the conjecture, it has to be thought as a coarse version of the grid minor theorem. So the grid minor theorem in graph theory, it states that if your graph that you consider, if you have a graph, either it has bounded treewidths, or if it has large treewidths, then it must have some large grid as minor. Okay, and this is coarse version. So now it states that a graph, there are two possibilities for an infinite graph. Either it has finite treewidths or bounded treewidths, or it has every finite k times k grid, finite grid, as asymptotic minor, okay? And there is one direction, so which is quite easy. So it's quite easy to see that if you're quasi-isometric to a graph of finite treewidth, so we can just see it together. If I take some graph G, I'm just claiming that if G, that the inclusion from the bottom to the top is true. So by this I mean that if J is quasi-isometric to some graph G prime, and G prime has finite treewidths, so then my claim is that J excludes some finite, right? Some finite grid as an asymptotic minor. And to see it, just see that G, you have G, you know that it's quasi-isometric to some graph G prime with finite treewidths. And this graph G prime, it has finite treewidths. So in particular, if you use Robertson-Simon theorem, you know that it excludes some grid. Some k times k finite grid as minor, but in particular, when you exclude some grid as minor, you also exclude it as an asymptotic minor. So it excludes some k grid as. Okay, and now you know that J is quasi-isometric to a graph which excludes some grid, finite grid as an asymptotic minor. And this property, I just told before that it was preserved under taking quasi-isometry. So in particular, G also excludes some finite grid as an asymptotic minor. So this inclusion from there to there, it holds. But the other one, it's quite open. And I have no idea whether it's true or not. It's true in some class of group. In all finitely presented groups, it was proved recently that it's true. Okay. I don't know much more about this. And okay, and now if we sum up all the results that we saw until now with weak cup number, it exactly states that, okay, recall that whenever we have some graph, which is quasi-isometric for graph of finite fluids, it has bounding weak cup number, and we even have the tightest possible correspondence. And if we combine it with this result now, we know that in fact the class of groups, of graphs, with a finite, bounded finite weak cup number, it's exactly something sandwiched between these two classes. And these two classes are supposed to be equal. We don't know if they are equal or not, okay? And so it raised two very interesting questions. Let's say intermediary question in order to tackle this big conjecture. So this class corresponds exactly to one of these two classes, and this we have no idea. And we can even ask, we even have for the stronger question of, we don't have any counterexample. In fact, if we want like some functional dependency between all of these parameters, right? We don't even know if like this kind of inequalities they are optimal or not. Like, if I, for example, if I have a finite weak cup number, does it mean that I always have some finite asymptotic minor, whose treewidth is exactly my weak cup number? This kind of thing we don't know, and this gives rise to a lot of interesting, like intermediary, let's say, questions to tackle this big conjecture of Georgakopoulos and Papasoglou. And okay, so I had some slides just to prove. Okay, so the proof of the exact lower bound in treewidth, there's a lot of trick. It took us some time, like really, to find it. So I don't plan to show it. I had some slides to give some ideas about how to still find linear lower bound in treewidth, but maybe I will skip it because still, like, we have to introduce heaven everything, and maybe there's still some stuff that I want to talk about. So how much time do I have now? 10, 15?
Wait, it's 25, so 20 minutes actually, at most.
Let's skip this part, I think, because I'm afraid that takes too much time. And I think some people are fed up, so... Okay, so let's...
Maybe you.
No, I'm fine. Okay, so maybe first thing, let's look more at the interesting corollaries about these results, okay? So first thing is that, okay, there's this result. So remember that whenever we are quasi-isometric to a tree, we have weak cup number equal 1, right? And strong also. And now, the funny thing is that there is this result of Georgakopoulos and Papasoglou. In fact, we are quasi-isometric to a tree exactly whenever we exclude the triangle as an asymptotic minor, okay? It's case 3. In fact, using this case 3, it has treewidth at least 2, right? And so if we combine just these two results together, it gives us exactly an exact characterization of all graphs with weak cup number equal 1. So the graph which look like trees, so which are quasi-isometric to trees, they are exactly the one with weak cup number equal 1. So this was also proved with completely different method by Appenzeller and Klinger. In fact, in its own, we don't really need this result to prove it. There is quite a simple self-contained proof of this result. But it's nice just to see it as a corollary of this more general theorem, I guess. And if we look at the level of groups, so if we come back to our world of K graphs, okay, so also like the class of groups with finite treewidth, it's quite a well-known class. It corresponds exactly to the class of what's called virtually free group. Okay, so let me maybe just start explaining what's free group. Okay, so the free groups, they are exactly the one who have some K graph of this kind. So who have some K graph with a tree with even degree. Okay. And this is a possible definition of free groups. So maybe this one, people from group theory, they won't like it, but this is one that we can take, okay? And virtually free group, it's exactly some group which contain such a subgroup, okay? So some group which has some tree of even degree as a subgroup, but a subgroup of finite index, okay? So in some other words, it means that your KD graph of your virtually free groups, you can decompose them by taking a finite number, superposing a finite number of disjoint trees, okay, and you can cover them like this, okay, in some way. And these virtually free groups, they were very well known for quite a long time ago, and they correspond exactly to the group which are finite treewidth. They correspond exactly to the group which are who has some tree in their quasi-isometric class of KD graph, okay. And it gives now as corollary. In fact, we can obtain the following corollary, okay. So now of this result, sorry. There's now a new characterization of finitely generated virtually free group. It's exactly the one with weak cop number 1. Okay? And this answers to the positive sum question, in fact, in the initial paper of Lee, Martínez-Pedroza, and Rodríguez-Quinche. And there was another question related, which is quite fun, and which is now, if we take a group, a Kelly graph, okay, a finitely generated group, we know now that whenever its weak cop number is 1, it must be virtually free, okay? But the thing is that does there exist some group which has a weak cop number neither 1, neither infinity? So for graph, we saw a lot of examples of such graph, okay? But whenever we have a lot of symmetries, so whenever we look at transitive graphs, does there exist intermediary weak cop numbers? Those symmetry break the fact that you must be either 1 or infinity. And quite recently, Florian Lehner, he had a positive answer, so he brought a positive answer to this question. And he showed that indeed it was the case. So that's quite a fun result. So in particular, so it gives, if we combine all of this together, it gives the following. It means that if we look at groups, so now a group, it has finite weak cop number, if and only if it has weak cop number 1, if and only if it is virtually free. Okay, all of this we can branch them together. Okay, and I have to mention now, okay, now I would like to start talking a little bit about the strong cop number, because we talk only about the weak cop number for some time. And the same question also we can ask it, does there exist some groups with intermediary strong cop number, and it's still open. And for strong cop number, we understand quite bad what happens now. We understand a couple of things, I will show you in a moment. But this question is one of the most important, I think, question which is open now for a strong cop number, okay? Okay, let's talk a little bit about strong cop number for the next 5-10 minutes, and then I stop. So, okay, the first thing is that, okay, if we look at the grid, it was unknown until now what the strong cop number of the grid. So the weak cop number, it's infinity, and using this asymptotic minor result that we had, these lower bounds, it could be a way to see it. But for strong cop number, it was a question in the original paper, what was its cop number? Was it finite or infinite? And we proved that it's infinite, okay? And okay, it was proved also independently by Appenzeller and Klinger, so I won't give you a proof. Which is just more a first result about strong cop numbers. And there are in fact many proofs. So I think we have 2 or 3 different proofs, and they also have 2 or 3 different proofs. And by talking together and combining results, we just managed to find 3 proofs, combining all of our tools, their machinery and ours. So that was quite fun. And now let's look at who has finite strong cop number, but doesn't necessarily have finite weak cop numbers, okay? So let's try to distinguish the 2 parameters. And so, okay, so in graph theory, if I tell you what does it mean for a graph to looks like a tree, first thing that you will answer me is, okay, it means that you have finite treewidths, right? And we have these treewidths which measure how close a graph is from a tree. And now, from the perspective of metric space, there is some kind of analogous notion which was introduced by Gromov, and it's the notion of hyperbolicity. So a metric way to say that now a metric space, or graph also, if I equip it with this shortest path metric, looks like a tree, is to say that it's hyperbolic, okay? So what does it mean to be hyperbolic? So hyperbolicity is something that was introduced by Gromov. I think he gave like 20 different characterizations, something like this, of different flavor of hyperbolicity. So here's one of the most famous of it. So I'll say, so if I fix some parameter, delta, some positive, some non-negative parameter, I'll say that a graph or metric space, it's delta hyperbolic if for every triple of points, if I take any 3 shortest paths between them, and if I take any point on one of these 3 shortest paths, it will be in fact, its delta neighborhood, its delta ball will intersect one of the 2 other paths, okay? So it's some way, in fact, of saying that if I take any 3 points, and if I take any 3 paths, there's some kind of non-positively curved, my graph has some kind of non-positive, it's a generalization, a rough generalization of the notion of non-positive curvature, right? And my 3 paths, they should go like this. They should have some shape like this, if you want, some intuition about it. Okay. This is one of the most common, I think, definitions that you can find in terms of hyperbolicity. And the fun thing is that if you replace delta by 0, if you look at 0 hyperbolic things, 0 hyperbolic graphs, they correspond exactly to trees. If you take a tree, if you take 3 shortest paths, you can see that, in fact, you can choose this delta equal to 0, right? And this is an if and only if. Now in infinite graphs or in metric space, I will say that a graph is hyperbolic if I can find some delta, some constant delta for which it is delta hyperbolic. So every finite graph, again, it's hyperbolic because I can find this delta to be, I don't know, its number or its diameter, let's say, whenever it's connected. But whenever, and so it makes sense really, just this notion of hyperbolicity by itself, it just makes sense whenever I just focus on infinite graph, right? Okay, so here's an example. So it's a tessellation, a nice tessellation of that hyper.
Go back to so pi is a distance that moves delta from the union of the previous other p.
Yeah, so that's a compact way of writing it.
So what does it mean? I mean, because the pi
so I fix
shares vertices with the other p's, so it's in distance 0. How should I understand this?
Yeah, but it's every. Oh no, sorry, it's not pi. It's every point of pi. Sorry, I was too early when I did this.
I got it.
Okay, so if I take these three paths, and if I take any point on my graph, it must be close from one of the two other paths. And yeah, now just the path, it doesn't make any sense.
Yeah.
Because of its endpoint. You're right. Sorry. Hope it's clear for everyone now. Okay. So here's an example, quite famous drawing of a hyperbolic graph. So it's some regular, some tessellation of the hyperbolic plane, right? And you have also trees, which are zero hyperbolic. So they are another example of hyperbolic graphs, okay? And okay, a very nice and very fun results of in the initial paper on this Cops and Robert. It's the following. If you take any hyperbolic graph, then it has a strong Cope number equal to 1. In particular, it's a way to distinguish strong Cope number from weak Cope number. Because if we come back to this guy, it means that this guy has strong Cope number 1. But we know that this guy, in fact, it doesn't have finite treewidth. It doesn't have, in fact, it has a lot of grids. So this guy has an infinite weak Cope number, right? And a way to see it is that we can find, in fact, infinite grid as asymptotic minor in this guy. So I have to work a little bit to find them, but they exist, right? And so, okay, so this is quite a nice result, which illustrates quite well the fact that, I mean, it was not obvious from the definition, but that these two games, they doesn't behave exactly the same, right? And what we proved, and that was proved also independently by Appenzeller and Klinger, in fact, it's exactly like the weak Cope number, this notion of looking like a tree. In fact, it's exactly characterized the graphs with strong Cope number equal 1. So another way to state is that the graph has strong Cope number equal 1 if and only if it's hyperbolic, in fact. And okay, small comment, so maybe you don't have to read the statement here, but just that such a result, so characterization of hyperbolic finite graph, delta hyperbolic, when you fix this constant delta, it was already known. So by combining two works of Chalopin, Chepoi, Nisse, Vaxès, and Papasoglou and Pecatte, it was known, but it's also only worked in finite graphs, and they managed to characterize what does it mean to be delta hyperbolic when you fix your constant delta by means of pursuit evasion this time, Cops and Robert game, and the relation between your hyperbolicity constant. So you have two different speeds again, one for the Cop, one for the Robber, and they managed to characterize it by like connecting the hyperbolicity constant of a finite graph together with the difference of speed of the Cop and the Robber. Okay, and it's only with and it's with k-cops, I mean. Okay, but I won't say more about this. But the point is that the characterization, it's again an pursuit evasion game. It completely fails whenever you transpose it in infinite graphs, right? And so this previous result, you can see it as a rough generalization, in fact, of this group results that was known in a finite graph. And so, okay, so I had some slides on the proof, but maybe I don't want to kill you now with this. So our proof is not very hard.
It's fun.
Huh?
It's fun.
Do you want to hear about it or?
No, maybe not.
Okay. The only thing I want to say about the proof is that, in fact, the harder thing was to find the nice characterization of a hyperbolic graph. And once you know this nice characterization, and this is very important, this is something which is very central in Gromov work, and it's a central property. It's that whenever you're hyperbolic, you satisfy what we call a linear isoperimetric inequality. And what does it mean? So I'm just translating this characterization of hyperbolic graphs. If I have a graph which is hyperbolic, I know that there exist two constants. So how did I call them? D and K. I can always find them. Such that if I look at every large cycle, so large just means cycle of size at least, it was K or D, I confirm. Okay, K. And if I look at any subpath of these cycles of length K, D this time, so at least D, then I can find some shortest path in the overall graph between its two extremities. So something of size at most D minus 1. Okay? And why does it give some kind of linear isoperimetric inequality? Why do I call this kind of thing a linear isoperimetric inequality statement? Because in fact, now if you apply it a lot of time, in fact, so if this cycle that you obtain by replacing this path by this subpath of size D minus 1, if you apply it again, you can still find another subpath, replace it by a shorter subpath, do this like this, and at the end, what you obtain, so it's called a Van Kampen diagram, but you can see it as some kind of tiling, right? And you'll obtain some tiling, in fact, of your initial cycle, and where each tile, it has bounded length, okay? All these cycles, they have lengths at most 2D, okay? And so this statement, in fact, it exactly states that if you're in hyperbolic graph, you can find some constant D, such that every large cycle, okay, you can type them, in fact, by using just a linear number, and linear, by linear, I just mean with respect to the size of my initial cycle, right? By a linear number of smaller cycles, and smaller cycles, very small cycles of bounded size, okay? And once we have this characterization, in fact, this statement, it gives us a fun proof of this statement, this if and only if, I mean, the reverse direction. The fact that if you have a strong cop number 1, then you're hyperbolic.
So you have to stop the tiling when you reach K, right?
Yeah, when you reach K. So if you take now, if the size of your tiles you want to tile your cycle with, you set it to be the maximum between D or 2D and K, then you find some tiling of any big cycle with tiles of constant size. In fact, it's even an if and only if. It characterizes exactly hyperbolicity, this thing, in groups and also in graphs. And that's quite fun. That's a big result from Gromov. And okay, once you have this characterization or this linear isoperimetric inequality, so we obtain a fun proof, but I think I will skip it, of the thing I mentioned. So okay, so let me conclude now. So okay, just to sum up, so for weak cop numbers, we know that we can sandwich them between the treewidths of their asymptotic minors, finite asymptotic minor, and the treewidths of everyone which is in my quasi-isometry class, okay? And if the conjecture of Georgakopoulos and Papasoglou turn out to be true, then we should have inferred some functional dependency between this parameter and these two ones on the left and on the right, right? And so it's still open whether just it's equivalent having finite weak cop number and having finite any of these two parameters. And it's one of the big questions now that remains after this work. And yeah, so we have characterization of weak cop number, strong cop number equal 1, okay? And there is also this quite fun question from the original paper of having finitely generated groups with intermediary strong cop number. And there we have, in fact, a lot of other questions, but I think I will stop there. Thank you very much.